Alright, so today we are going to begin Part C of our separations homework. And what we're going to be working on today is we're going to derive our Fensky equation and our Underwood equations, which look at the reboiler or bottom portion of a distillation column. And then once we have derived those two equations, we are going to move on to determining the minimum reflux for an equimolar four-component feed at given relative volatilities. And so we'll code up what that is supposed to look like in Colab. So to get started, we want to derive our Fensky and Underwood equations. And I want to start off by kind of just giving a little background on what exactly we're looking for. These are not going to be even, but that's okay. It's just not, rectangles can be hard. All right, and so we have our vapors moving up from our reboiler to our condenser. And so we have our condenser labeled C and our reboiler labeled as R. So really it's just a super simplified version of a distillation column schematic or drawing. And so what we can do now is we can look at what we consider our light key, which is our lighter components, and our heavy key, or our heavier components. And we can write out equations for both, where we have the composition of our light key and our reboiler is equal to our light key K value times our liquid composition of our light key and our reboiler. And then we can do the same for our heavy key, where we have our heavy key and our reboiler is equal to the K value of our heavy key component multiplied by the liquid composition of our heavy key component in our reboiler. And so the next thing that we can see here is we can divide both these equations. And we get our k values over each other. And we can remember that when we have kx over ky, or vice versa, that is equal to our relative volatility. Now, relative volatility for this portion of the homework will be with respect to our heavy key. And so rewriting this, all right, and so rewriting this with the divisions here, we have y light key, our vapor component of the light key in our reboiler, divided by the composition of the heavy key vapor in our reboiler. Remember that's for reboiler, equals our alpha value, that is our light key divided by heavy key, and I'll express that like so, just so we remember. And so we have x for our light key divided by x for our heavy key, and this is all in the reboiler. And to clean this up, we are going to get rid of these reboiler terms here, so it's just going to be light key vapor over heavy key vapor is equal to alpha times, and there we go. All right, and now this will lead into what is known as our Fensky equation. And we're going to use this bottom part here similarly for when we get into the Underwood equation. So to get our Fensky equation, we're actually going to look at the liquid portion, and we can actually flip this around to get something similar. And so what we have is we can do the liquid composition of our light key, but what we also want to look at is the shelf underneath it. So this is going to be n minus 1 from our starting point. And our starting point is, I guess we really just pick, and we identify that as n. And so what we can do is we have our heavy key underneath, and this will be also n minus 1 because your liquid is going to be one step down compared to your vapor, which would be up 1. And so we can set this equal to, we end up with alpha squared multiplied by the heat of vaporization over light key over h over heavy key. And again, this is all in the reboiler. All right, and so now what we can also do is we can write we can write an equation out for our distillate. And our distillate is at the top of our distillation column. So we have our light key and our distillate divided by our heavy key and our distillate is equal to alpha to the n multiplied out by the light key at the bottom and our heavy key at the bottom. So now what we can do is we can divide our distillate equation. Yeah, we can divide our distillate equation by our boiling equation. So what we get is we have x light key distillate over x heavy key distillate divided by x light key at the bottom, x heavy key at the bottom. And this ends up being equal to, we end up with n log alpha on this side. And it's a little hand wavy, but it's for the sake of speeding up this derivation. And so now what we do is it's pretty straightforward from here, actually, is we can take, there should actually be a log on this side here. So now what we can do is we can take, really just divide both of these sides by log A. And now these cancel out, and we are simply left with, I'll write this out just for the sake of the video here. See if x light key, and the distillate, x heavy key, distillate, divide all that, over light key, over a heavy key, at the boiler, or at the bottom, sorry, not the boiler, and this is all equal to n, or the number of stages we need in our distillation column. So this here is our Fensky equation. So now we'll move on and go ahead and derive our Underwood equation. So for our Underwood equation, we need to look at the pinch point on our plot. And so when we draw out this plot, just to give us a little background here, we have our operating line, we have our equilibrium line, our reaction line, and now what we do is say we pick this point here. We'll go down further. We pick this point here. And then this point makes almost a triangle here. And then we come down to say a point here, for example. And now when we find these steps, or how to find how many shelves we need in our distillation column, we usually look at this line similar to this. But you can see it approaches this point here, and this is our pinch point. And the Underwood equation really helps us evaluate truly how many steps, or not how many steps, our composition Y at a point such as this. And so we're going to start this off by writing out our equation where we have the vapor of our y component at n plus 1 is equal to the liquid times x at a given I, and then at our starting point, plus our distillate times x at a given I, and this is our distillate. Okay? And this should be yi. And so we want to rearrange this xi here, and we we can do that by recalling that our yin is equal to our ki multiplied by our xin. And we rearrange this to get xin equals, trying to algebra this, yin over ki. And that's what we're going to plug in here. So rearranging this, we get vyi is equal to L times yi over ki plus our distillate multiplied by x in our distillate. Okay? So now what we can do is we can move these on the same side and factor out. And when we do that, we get v minus, it should be L over ki, well, factor out a yi equals dxi in our distillate. And so moving forward, we get yi by itself. So dxid divided by everything in those parentheses. Something like that. Okay? And so here's where we get into the annoying part that they usually do, and it's called their traditions for this Underwood equation. So what we want to do is we're actually going to multiply by ki on the bottom and the top. And so what we're left with is y sub I equals ki dxid, and that's all divided by vki minus our liquid. And so, fully rewriting this out, we divide by yet another tradition where we divide the top and bottom by k sub r. And so we're left with ki over kr dxi, comma d, and that's all divided by v ki over kr minus our liquid divided by kr. And what we see from what we've previously done is we have this ki over kr here and here, which we can correlate to our relative volatility. So we simplify this out, we get our vapor times our yi. It's equal to alpha I, or with respect to I, because I is on top, dxi, comma d. And then we have, on the bottom, we have alpha, and then we have minus L over VKR. And so finally, what we can do is we can pull this out. We pull out the D, and we can take the summation of alpha I xi comma d, and we divide this by alpha I minus our phi. And our phi is another tradition, which is just a fancy way of writing that fraction. All right, and so now we have just derived, well, you can call it here, and this is the Underwood equation. All right. So we've derived our Underwood and our Fensky equations. So now we're going to go into Colab and look at a four-component mixture and code up an example visually for better understanding. All right, so now we're going to code this up in Colab and find the minimum reflux for a four-component distillation column. So to start off, we have a constant relative volatility, so we need to pull those from our library and from the given problem where we have 2.5, 2, 1, and 0.7. And we want to set f equals to 1. Not as integer ratio, stop. And then we have z equals np dot array. Oh. And this is going to be 0.25, 0.25. Yeah. 0.25. And then we have a Q value, or our, where's it at here? Our liquid feed fraction of 50%. So that would be 0.5. Oh, and we have a typo, of course. It's not a coding assignment. There's not a typo involved. And now we need to define a couple more variables here. So we have LKIDX, which is equal to 1. And then we have HKIDX, which is equal to 2. And we have RLKD, which is equal to 0.95, or that is our recovery. And so we have our other recovery, which is our heavy key at, I believe it was 96%. And so what we need now is WD equals our F times NP dot R underscore. We want to do LKIDX. Oh, missing parenthesis here. LKIDX. Need a colon. Okay. And then we do RLKD times Z multiply it out here by LKIDX. And then we have 1 minus our HKB. This is multiplied by Z. This is multiplied by HKIDX. And we have comma, then 0 to eliminate this. We have 0 times Z. And then we have HKIDX plus 1. We have a typo here somewhere, it seems. And that is because this needs to be that. And then we need to come over here and replace that here. No, it's still saying we are having an issue. So the issue was we were missing a Z here for the final portion of that. Alright, and so we are going to shift enter and see if it works correctly, and it did, which is fantastic. And so now what we're going to go ahead and do is we need to define our phi value for our Underwood. And we want to return the JNP sum of alpha times Z divided by alpha minus phi. And then we do this minus 1 minus Q. Okay. So now what we can do is we can vectorize this. We have Underwood underscore vector, which equals jax.jit, so it runs faster, jnp.vectorize, Underwood comma, signature equals. Okay. Shift enter there. And now we do the usual where we have fig equals make underscore sublets. And now we have our phi's as well, which is np.linspace 0.9 times np min of our alphas. And then we have 1.1 times np max of our alpha, and then 1,000 points. And now we have fig add underscore scatter, x equals our phi values, our y equals our Underwood underscore vector, and phi's. Alright, and then we need to update our axes. Update y-axes. Range, to make it nicer, we want to go from -3 to 3. NP linspace is not defined. That's because, again, we're missing a component to that. Alright, so now we have a nice plot, and we'll come back to that once we do our phi underscore root, where we need to optimize it in the scalar direction. And we'll do Underwood, comma, x naught equals 1.5 dot root. Shift enter, and now we need to find our minimum reflux ratio, which was the purpose of this assignment. That's np.sum alpha times xd divided by alpha minus phi underscore root minus 1. And we want to print our minimum reflux ratio. We didn't define xd anywhere, so we didn't forget to define xd here. Our distillate where we have wd divided by np.sum over wd. We run all that, and we can see that we have determined our minimum reflux for an equimolar 4-component feed at 1.65. So that is our the minimum reflux. And so we also derived the Fensky and Underwood equations as well, and we were able to see how those correlate, especially to pinch points and their locations within the distillation column. So thank you guys for watching.